Okay, let's dive into this because we've got a really cool puzzle today, one that comes straight from the world of programming. It's kind of like a tale of two twin algorithms. They look almost identical, but one of them is a world-class sprinter and the other, well, the other one is stuck in molasses. We're going to figure out why.
So, right off the bat, here's the central mystery. How can these two functions, which look so simple on the surface, be so wildly different when it comes to speed? What's going on under the hood that turns one into a speed demon and the other into a total slouch?
All right, take a look for yourself. On the left, we've got a function for the natural log of a factorial, and on the right, a classic, a function to calculate a Fibonacci number. Now, they both use this thing called recursion, which just means the function calls itself. And here's the weird part. The factorial function is super fast, no problem, even with big numbers. But the Fibonacci one? Oh man, it slows to an absolute crawl. We're talking it takes forever just to calculate the 50th number. So, what gives?
To solve this mystery, we've got to put on our detective hats. We're going to follow the trail of breadcrumbs, the actual calls each function makes, to see what's really happening deep inside the machine.
Okay, first, a super quick refresher on our main clue here, recursion. The best way to think about it is like a set of those Russian nesting dolls, you know? To solve a big problem, the function opens it up and finds a slightly smaller version of the exact same problem inside. So it calls itself to solve that one, and so on until it gets to the tiniest little doll, a problem so simple it can just solve it instantly.
Now, let's trace our speedy factorial function. When you ask it for, say, the factorial of 5, it makes just one smaller call, to the number 4. That call then makes just one call to 3, and on it goes. See? It's a nice, clean, straight line. Super efficient, very direct, one call leads to the next. No drama.
But now, let's trace the path for Fibonacci. And this is where things get really messy. Instead of one single, neat call, each step explodes into 2 more calls. It creates this huge, sprawling, branching tree of work, not a straight line at all. And if you look closely, you'll see the real problem. It's doing the same calculations over and over and over again. To get Fib5, it ends up calculating Fib3 twice and Fib2 3 times. It's just wasting a ton of time redoing work it has already done.
And that insane branching tree of repeated work, that is our smoking gun. We've found the culprit, the source of this massive slowdown. Now let's just look at the evidence to see how bad the damage really is.
And wow, the numbers do not lie. Check this out. On one machine, calculating the 40th Fibonacci number took 22 seconds. Okay, not great, but bumping it up just one notch to 41, it jumped to 35 seconds. And 42? Almost a full minute. You see what's happening? The time isn't just creeping up, it's exploding.
And that's the absolute key to this whole thing. The time isn't just adding up bit by bit, it's multiplying. For every single number we add to the input, the amount of work pretty much doubles. And that runaway train is the textbook definition of exponential growth.
You know, in computer science, there's a shorthand for this called Big O notation. It's kind of like a performance rating for your code. Our speedy factorial function, that's what we call O of n, or linear. It means if you double the input, you roughly double the work. It's like deciding to walk 2 miles instead of 1. No big deal. But our slow Fibonacci function, that's O of 2 to the n, or exponential. With this, if you just add one more number to the input, you double the work. That's not like walking farther. That's like setting off an explosion. And that's the source of our huge performance gap.
All right, so we've totally cracked the case. The problem is a ridiculously inefficient algorithm that just recalculates the same stuff again and again. But you know, in programming, finding the problem is half the battle. So now, let's look at the beautiful, elegant solution.
And that solution has a name. It's a super powerful idea called dynamic programming. And honestly, the core idea is so simple it's genius. It's basically, don't be dumb. Don't solve the same problem twice. If you figure something out, just write down the answer. Solve each little piece of the puzzle just once, save the solution, and if you ever need it again, you just look it up.
So here's what that fix actually looks like. This optimized code builds a list of answers from the bottom up. To find the 10th Fibonacci number, it first finds and stores the answers for 1, then 2, then 3, and so on. So when it needs a previous value, it doesn't have to set off that massive tree of calls. It just looks up the answer in its list. All that repeated work? Poof, it's gone.
And the result?
The difference this makes is it's staggering. It's not just a little bit faster. Remember how the original code took almost a minute for FIB42? Well, get this. The source material says that with this new, smarter approach, calculating even FIB100 would take just a fraction of a second. That right there is the power of a good algorithm.
So, we solved the mystery of the slow Fibonacci function. Awesome. But this whole story isn't just about one little math problem. This tale of two algorithms actually shows us a really fundamental rule for how we build good, efficient software. For everything.
Yeah, this pattern of overlapping, repetitive problems, it shows up everywhere. Think about your GPS trying to find the absolute fastest route, or a vending machine trying to give you change with the fewest coins possible. These are all problems where, if you're not careful, you can fall right into that same exponential trap. Knowing how to spot it and avoid it is absolutely critical.
So if there's one thing to take away from all this, it's this. What seems like a tiny, harmless choice in your code, like calling a function twice instead of once, can be the difference between a program that spits out an answer instantly and one that would literally take longer than the age of the universe to finish. It's a powerful lesson in why it pays to think before you code.
And that kind of leaves us with one final thought to chew on. We've seen how a function that looks totally innocent can hide this massive explosion of complexity. It really makes you wonder, right? What other simple-looking problems out there are actually just computational icebergs, with almost all of their danger hidden right beneath the surface?